This is an introductory video for FNets about what they are, why they are, how they're portably efficient across parallel and sequential platforms, and how they improve correctness of concurrent programs. At the end, we'll get into why FNets are not enough, and that will get us into the next step, which will be scalpel to fill in the blanks. But this will hopefully provide the motivation for that next video. So first, to describe what FNets are, we'll describe what they're not. They are a way of getting different parts of a program to work together. Traditionally, a programmer starts by deciding what kind of platform the program will run on. If it's on a sequential platform, they'll typically use a standard sequential language. If it's on a distributed platform with high latency between the nodes, they'll use some sort of message passing between individual sequential programs. And if it's more localized on a multi-core or otherwise shared memory platform with low latency between the nodes, then they'll use shared memory and locks between individual sequential programs. But still, they'll use individual sequential programs and communicate between them. In those cases, concurrent communication is an emergent phenomenon. That is, a communication is not a single thing in the program that you can point to in either message passing or shared memory. Instead, it's the result of two or more different processes independently doing something which results in the communication. And that makes it so that communication may easily take place when it's not desired, and if not careful, the wrong parts may communicate. And the parts that are involved in the communication may actually depend on the timing in the individual processes, so that if one process gets to a certain point before the other one, then one kind of communication will occur, otherwise another kind will occur. There's also instances of deadlock where different processes are waiting for the other one to do something. So there's all kinds of different things that can go wrong. And a lot of that is because we're not dealing with the communication as one entity. We're dealing with it as this emergent phenomenon that will only occur if each process is doing the right thing at the right time to interact with the other process. So why do we use message passing for high latency platforms? Well, a message can contain lots of information. So with message passing, the latency is experienced just once to send all that information across the interconnect. The sender can start moving the information to the receiver before it's even needed at the receiver, and that means by the time the receiver needs it, it may already be there, and that's called latency hiding, actually getting the communication to occur while all of the processors are busy doing other things. There's also problems, especially on low latency systems. There's always one overhead copy required for each transfer. That is, the sender usually assumes that they will retain a copy of the data even as the receiver also gets a copy of the data. It's also clumsy when one can't predict what the next reference to the data will be. So the sender won't know who the receiver should be. The sender has to hang on to the data until it gets like another message telling it where the data should go, and then it can send it there, or it can send it to all the potential receivers and potentially exact some additional overhead in that process. Also, different kinds of message passing will sometimes result in blocking of a send if there's no room on the receiver to actually store the message. And that blocking may happen unexpectedly, and therefore a program may go from a correct to an incorrect program without having any formal reason why that error occurred, especially since that lack of space on the receiver can be a temporary situation. Now, why would we use shared memory for low latency communication? Well, it's just memory, so it's obviously a very natural way to interact, to have both of them interact with the same memory, just as different people in a room might interact on a whiteboard, on a shared whiteboard, or any other shared medium. A lock can also be modeled with memory so that the different processes can coordinate A lock might be called a token. You may think of a token on the memory that a process must pick up the token before it's allowed to access the memory and put the token back. And that allows only one process to access the memory at a time. Then you can have read locks where as many processes as want to can access that token for reading, but if any process wants to write to the memory, then it would have to have a special token which can only be gathered if no other processes have the read token. Now, with this kind of model, there's no need to predict where data should be ahead of time. Whoever gets to it next just gets to it next on a demand type of arrangement. And shared readers is very easy without the overhead of additional copies. Essentially, each process is making very small accesses to low latency memory and just getting as much memory as it needs. But it's easy to mess up if you don't respect the lock protocol. There's no buffering unless you explicitly buffer within it, so that if one process is reading and another process wants to write, the writing process has to just wait for the reading processes unless you put some extra programming into it to handle that situation. And that might very well be modeled as a message passing situation. If it is used in a high latency environment, then you've got the issues of either suffering the latency for each access of a small memory or trying to model, trying to access larger pages of data each time on each access, and then you have memory consistency problems where one process might have the data that another process wants to be accessing, and you can either get ping-ponging of large data sets or inconsistent data on each processor. Neither one of them, therefore, fits all situations. Essentially, the programmer has to know before they start programming how much latency to expect on the target platform. And to optimize it, they may even need to know how many processors are on that platform and how they're configured. And there may be high latency between some and low latency between the others. So they might have to optimize by using some shared memory, some message passing. And if multiple processes will be sharing some of those processors, then some of them may end up running slower. And in fact, we may need to make assumptions about how fast each processor will run in order to optimize communication so that things aren't waiting around. There's all kinds of issues. And it's often impossible to know all that in advance. Those factors may even change while the program is running. So these are not optimal. There are hybrid approaches. Partitioned global address spaces, or PGAS, is a little bit similar to what we'll deal with here, only we'll try to provide a clean interface to that'll be more correct. And then cooperative data sharing is actually a system that's similar to both shared memory and message passing that actually came out of the FNET's work that I'll describe here, but I won't go further into that. So now, what are FNETs? So they're a surprisingly simple solution to this problem. An FNET is usually represented as a network on a piece of paper, that is graphically. It is a collection of functional transformations which are just sequential programs. That is, any sequential program, as long as it's deterministic, is essentially a function, a partial recursive function from inputs to outputs. We will call these transformations tactics. So you can think of them as programs, you can think of them as subroutines, you can think of them as functions. I don't care, but we'll call them tactics. All that's required is that they're deterministic, that is functional, from their inputs to their outputs. And they're shown as circles, which interact through shared regions, which we'll call resources, and those are shown as rectangles. And then arrows connect the circles and the rectangles. An observe arrow goes from the resource to a tactic, that is from the rectangle to the circle, and it means that the resource content is the input or argument to the tactic. It's an input. If the arrow goes the other way, from the tactic circle to the resource rectangle, then it's called replace arrow, and that means that the resource is an output or result of the tactic, and it means the entire content of that resource is a result, not just part of it. If there are arrows on both ends, we call that observe, replace, or update, and that means that that resource is both an input and an output to the, or maybe both an input and an output to the tactic, and it's also what you use if you're only doing a partial replacement, that is, if only part of the resource is an output, because that's the same as if the tactic had observed the entire resource and then replaced part of it and then replaced all of that onto the resource. So both ends means update, and that can also mean partial replacement of the resource by the tactic. So that's the content state of the resources, but resources also have a control state, which basically plays the same role as a lock in many ways. The best way to think of a control state is as a colored token on the resource. So the initial control state of every resource is always green, like a green token. The control domain for a resource is often shown in the left side of the rectangle. The control domain is all the control states, that is all the colors that that resource might reach over its lifetime, all the different colors of tokens that might get placed onto that resource, one at a time. There will only always be at most one token on the resource at any one time. Where an arrow connects to the resource in either direction, colored access dots show the control states or control state, which will allow access of that resource by that tactic. So if there's a green dot at the end of the arrow, it means that that resource can only be accessed by that tactic if the resource has a green control state, a green token on it. As a result of the access, the control state may change. That is, the token may change, the color of the token, and the new control state dots, which are inside the rectangle near the arrow, those show the possibilities that that tactic may change that token to, the colors that it may change that control state to, the control state of that resource. So just by looking at those colored dots, you can both see the color or control state that that resource must be in order to be accessed by that tactic, and which control state that tactic may assign to the resource when it's finished. How does it all work together? So a tactic can only fire or execute or evaluate, that is, it can only do its thing, when all of its resources, that is, those connected to every one of these arrows of the tactic, are ready. And by ready, it means that the control state of that resource matches one of the access dots for that arrow. So if the arrow has a green access dot at the end, then that resource will only be ready for that tactic when that resource has a green control state. When the tactic fires, that is when all of its resources are ready, the control states disappear from all of its resource, basically atomically, all at one time. And then it gets access to all the resource, all the content state, and it can do whatever its arrows say that it can do. It can read from them. If it has observed arrowheads, it can replace the contents, or it can update the contents. It is evaluating then as a function as if it's got its inputs from its observe arrows and its outputs to its replace arrows. And whenever it finishes with a resource, it gives it a new control state, a new colored token. That is one that will match one of the new control state dots. And it'll put that token onto that resource. And once it's put the token there, it has no further access to the resource. And that's almost the entire model. There's just a few little more rules. Tactics cannot have any inputs or outputs except this way. So if you're talking about time of day, that time of day has to be modeled on a resource. If you're talking about inputs from the outside, the input has to be coming through a resource, etc. A file is on a resource. Tactics can't keep hidden internal state between each firing or evaluation. But if it wants to save state to have it handy for the next execution, it can easily do so by just putting it onto another resource, because resources can be update resources. So each time the tactic begins, it can observe that resource, do its thing, write the new state out to that resource, and then the next time it begins, that new state will be there for it to observe the next time. Now, some lines don't need any arrowheads. You don't need to put any arrowhead on a line, and that just means that that resource is used only for its control state. That is, its access dot is still there, and its new control state dots are still there. It's just that it won't use the content state for any inputs or outputs. I've described when a tactic can fire. I've described what will happen when it does fire. But I haven't really said when it must fire. So far, an FNet that did nothing would technically be following the rules. So we also add a liveness rule, and that says that if a tactic is continuously ready to fire, then it eventually must fire. Note that if another tactic is bound to one of the same resources and it fires, then this tactic is not continuously ready to fire because the token has left one of the resources. So the clock restarts for this tactic. There is no fairness rule, so if multiple tactics are vying for access to the same shared resource, one of them may win every time. It doesn't necessarily go back and forth between the two tactics. And finally, there's a rule called predictability, which sounds like it's hardly worth anything, but it turns out to be very important. And that means any line which has no replace or update arrows, so no arrowhead on the resource end, and for which all the new control state dots are the same color. In other words, there's usually just one new control state dot. So that's called a predictable arrow. If it has no arrowhead on the resource end, and if it has just one color of new control state dot. And in that case, we will say that the predictable arrow will always produce a new control state. So remember, tactics are partial recursive functions. That means they won't always complete. So they may start up for certain inputs and put new control states to some of the resources, but it might get hung up and not produce control states to some of them, and it might take a very long time to produce control states to some of them. But this rule just says for any predictable arrow, it will eventually produce a new control state to that. And since it has no replace arrowhead for that resource, we already know what the content state of that resource will be as soon as the tactic starts up, because it's not going to change it. And what's the new control state going to be? It's going to be the one that is the color of all the new control state dots, or the single control state dot. That's all the rules. That's the complete model. So we'll claim that these FNets, that model that I just described, are portably efficient, which means they have the nicest properties of both shared memory and message passing, and are more formal and easier to prove correct than either message passing or shared memory. We will not claim that FNets are very practical as they stand. It's more of a computational model than a programming model. You need all kinds of other things in it to actually make a language that's worth programming in. So how are FNets portably efficient? Well, for low latency and uniprocessor platforms, it should be pretty obvious that the memory model is efficient for those. I mean, it's just like shared memory. It just needs to get that token first, which is just like shared memory getting the lock on the resource before it accesses it. So there's nothing much there. But it may not be clear that this also allows for multiple tactics to read a resource concurrently, because we just said once the token is taken away from a resource, no other no other tactics are going to be able to access that resource because obviously their arrows are not going to be ready for that resource because the token isn't going to match their color because there is no token. So if one tactic is reading the resource, no other tactics can seemingly read the resource at the same time. But we're saying that's not true, and we'll describe how in a minute. And this also optionally allows for a tactic to create or update a next version of the resource while the last version is still being read by other tactics. And again, so that's like double buffering or avoiding a read lock stall. And we'll describe also how that works. And all that happens without any programming effort. And that's all with that super simple model that we just described of FNets. So how are they portably efficient for high latency platforms that message passing would normally be used for? Well, it may be obvious that if only one tactic can access a resource with a current control state, the content can be moved to where it's needed before it's needed there. That is to say, suppose a resource only has one tactic that is connected to it with a red access dot. Then as soon as the red token is placed onto that resource, we know that that resource content can move toward that tactic that's going to access it with the red access dot. It can be starting to move on its way before that tactic ever needs it because we know where it will be needed. However, it may not be clear that that tactic may be able to take that content and read that content, and another tactic on the other end may be able to create new content even while that tactic is reading the old content. Again, that's counterintuitive based on the way our token model said that things worked. But again, we'll describe that in a minute. And it may not be clear that the content can be sent or multicast to several receivers concurrently, and it may not be obvious that the resource contents may only need to move in one direction, not back and forth. These resources make it look like the resource contents are moving back and forth, but those arrowheads should be a hint that that's not necessarily required. So in other words, these can have all of the efficiencies of message passing in a high latency environment. So how are these all achieved? They're all achieved through predictability. That little rule about if all new state dots are the same color, new control state dots are the same color, and there are no replace arrows, the tactic will eventually produce a new control state for that resource. That predictability rule makes it so that just as soon as a tactic fires, the runtime system knows what both the new control state and the new content state of that resource will be. And therefore, the runtime system can prematurely give it that control state and allow other tactics to fire as though it's already been assigned, as long as the runtime system also makes sure that those new tactics which are accessing that resource don't mess up the content state, that they don't affect the tactic that's still reading or observing that resource. That means if the new tactics are just observing the resource, then the runtime system may let them move ahead at the same time. That's how you get multiple readers. The one resource, the one tactic fires, the runtime system says I can assign the new token back to that resource right away, even while it's still reading, observing it. And the runtime system says, now there's another tactic that also wants to observe it. I can let it start up too. It's not going to affect the content state. And therefore, both of those tactics can be observing at the same time, and that can go on and on and on for multiple tactics. Now in this example, tactic W can fire again, but it wants to replace the resource contents, and the runtime system cannot let it do that while they're being observed by the other tactics. Remember, it was only allowed to use predictability if it allowed things to run the same way that they would have run otherwise. The system can, however, let W run with a new version of the resource, since it won't be observing anything on the old resource anyway, and it can do that while the others continue to observe the old version. And then the runtime can discard that observed one when the observers are done with it. This is essentially buffering or avoiding a read stall if all of the tactics are sharing low latency access to memory. It may be obvious that control state addresses the same kinds of synchronization issues as both message passing and shared memory locks, and that the firing rule promotes latency hiding because it allows the information to move to where it's needed before it's needed there, because the control state not only says nobody's accessing this right now, there's a token on it, it also says, it also restricts who will access it next, who may access it next. And the fact that the firing rule makes it so that a tactic doesn't start up until all of its resources are ready means that it promotes latency hiding. That is, all of the resources can be moving to where they need to be while the processor is busy evaluating other tactics or executing other tactics. And it only needs to start on a tactic once all of its resources are there and available for it to get working. And then once the processor starts spending time on that tactic, nothing's going to slow it down. It's not going to wait for anything. It's going to get all of its work done right in that one execution. But it may not be obvious that maintaining these control states and implementing the firing rule of tactics has very low overhead. That is, we make it sound like every time a new token gets put down, new colored token, we have to go around and check every tactic that's connected to that resource and check all of its other resources to see if they're all ready, and only if they're all ready up for one of those tactics can it fire. Actually, we can reduce that overhead significantly. Instead of maintaining a control state for each resource and repeatedly checking all those control states to see when a tactic should fire, we can just keep a count of how many resources each tactic has that have the wrong control state. We call that a reasons count, and it is the number of reasons that this tactic is not firing right now. So initially, that count is equal to the number of access dots that that tactic has that are not green. Because if all of its resources have green access dots, then there's no reason it can't fire right away, and its reasons count is 0. There are no reasons it can't fire. So it's increased by 1 for each other color of access dot. Then, when a new control state is assigned to a resource, the runtime system just decrements the count for just the tactics bound to that resource with that new access dot color. And if any of those become 0, then that tactic can fire. So it turns out to be just a simple matter of decrementing, checking for 0, and then perhaps incrementing again. And those are things that computers are very good at. So how do FNets improve the correctness of concurrent programs? Well, for one thing, as we said initially, communications in other programs are not obvious. They're not a single thing, but here they are. Here, the communication are those arrowheads and those resources. Every FNet has a fairly obvious formal mathematical representation where each tactic is a partial recursive function from the content states of its observable resources to the new content states for its replaceable resources and the new control states for all of its resources. And that can just be expressed as a function. Tactics are actually total for their predictable results instead of partial recursive functions for those results, because predictable arrowheads say that they will always produce a result. This in turn gives FNets lots of nice properties. So any tactic expressing some partial recursive function produces the same possible behaviors. That means that when specifying a program, each tactic only has to have a functional specification about the mapping from its observable resources to the new control state for all of its resources, new content state for its replaceable resources. Any implementation that matches that functional specification is sufficient and will give the same behavior within the resulting program. That's very unlike many other forms of communicating sequential processes, where the behavior can also depend on the order in which the inputs are consumed and when the outputs are produced, what's going on in other processes, etc. This also implies correctly that tactics can be considered as occurring instantaneously and that they can't deadlock. So, as we're considering what's happening inside of a tactic, we only have to consider what's happening there. We don't have to think of any other tactics doing their thing at the same time, because each tactic is a simple functional mapping. It doesn't depend on what's going on elsewhere. So as we are considering what our FNet can do, we can go one tactic by one tactic by one tactic and just consider the different ways that those tactics can, the different orders that they might execute in, rather than considering what's happening in other tactics at the same time. It works for our single track mind. Also, the tactic languages themselves are generally standard sequential languages. So you might have C or Fortran or Python or whatever. That's what you might implement your tactics in. And normally, when you start throwing concurrency into things or parallelism, you suddenly throw out some of the rules of your language. Suddenly, memory can change when nothing in your process has changed it because it's being changed elsewhere, for example. Or your program may block and it may only unblock based on something that's happening somewhere else, and therefore that's not part of your standard sequential language definition, the semantics of your sequential language. But in FNets, it preserves all that. Nothing's going to change out from under you. Nothing's going to block you as you're executing. You can rely on your sequential language semantics when you are reasoning about how each tactic works. So existing sequential language descriptions or denotational semantics can be used as is for programming and proofs. Non-determinism often creeps into other parallel programs undetected and may completely complicate replay of debugging significantly. That is, your program may not work this time, and then you may start up the debugger and suddenly it works every time, and then you turn off the debugger and it stops working again. Sometimes those are called Heisenbugs after the Heisenberg uncertainty principle. So just adding tracing or just adding checkpointing to your program may change whether it works correctly anymore, and it may come and go. FNets can be analyzed statically, and many can be statically recognized as being deterministic always, and potentially non-deterministic ones can be easily and efficiently automatically instrumented to say where those non-deterministic choices are being made, so that if you need to replay it, you can replay it with exactly the same non-deterministic choices made, and therefore with the same results. That same approach can also be used to optimize checkpointing and recovery, because, for example, as long as you have a checkpoint of some certain place and a record of all of the non-deterministic choices that have been made, if something goes wrong after that checkpoint, you can re-execute with exactly the same results. So, FNets have lots of desirable properties. It may make you want to say, fine, let's start programming now. But I hope it's kind of obvious that this is a very limited model here. It's completely impractical for programming. Um, there's not even any way of really getting input or output into this kind of thing that I mentioned other than just starting that input as some of the contents of some of the resources and looking at the contents of other resources for the outputs. So providing external inputs and outputs, there's no arrays here, there's no dynamic resource allocation, there's no data parallelism, there's no modules any higher level than tactics. So every module that we build our program out of has to have that kind of behavior that a tactic has, where it doesn't start until all of its resources are ready, and it's deterministic and it's stateless and it does all this stuff. Sometimes we need different kinds of modules. Sometimes we don't know what our modules are going to look like. We just want to start from a high level network and just build in modules or circles that are just abstract. We're not sure how those will be implemented yet, and then build those hierarchically. So we need top-down programming modularity. We need first-class FNets. We need libraries. We need dynamic linking. We need data abstraction. We need object-oriented programming. So none of that stuff is in FNets, and we need it all, and that's where Scalpel comes along. Scalpel is called Scalable Planning Language. The next video will describe that. That will add all that stuff to the basic FNets core, and that will turn this basic paradigm into something that's actually useful. But you need to understand the advantages from this video before you go on to that, because otherwise you're not going to understand the motivation behind adding all of these new programming constructs to this seemingly rather arcane model. Yes, it is arcane, but it's worth it because of the advantages that I've outlined here. And if you want more information on any of this stuff, there's a book, Scalable Planning by David DiNucci, that will have more on the theory. It'll go into all this stuff in much more depth and tell you how to implement, why to implement, and it will also go into Scalpel. Thank you.